So V and W, suppose both are vector spaces over some field F, okay, and T is a map from V to W such that it is compatible with addition and scalar multiplication. In other words, it is compatible with linear combinations. Okay. What does it mean? Suppose you take two vectors v1 and v2 both in V, and suppose you consider this linear combination of v1 and v2, apply T on this and you get A T v1 plus B T v2. Okay. So that's it. Put A equal to 1, B equal to 1, you get that it is compatible with addition. Put just B equal to 0, then A v1 is just A times T of v1. That means it is compatible with scalar multiplication. Okay. Okay, and here, let's see at first some examples. Example 1, you have seen this plenty of times, that is, consider a matrix, an m cross n matrix, say, over the reals. Then the multiplication by A gives you a map from Rm to Rn, right? Left multiplication by A gives you a map, because this one has, wait a minute, this is m cross n, and here you will have some vector, sorry, this is going to be something inside R m, right? So this is a map from Rn to Rm. Okay. That is left multiplication by A. Another example, maybe we write here example 2, because we do something else here. That is, consider this space Pnr to be the set of polynomials of degree less than equal to n with coefficients from R. Okay. Then this map differentiation d dt from Pnr to P n minus 1 R gives again a linear transformation. Okay. Is a linear transformation. Okay. So next we define coordinates. I'm not sure whether we have seen this term earlier. Even if we have seen this, let's just recall the notion. So suppose you have a vector space V. So V is a vector space over some field F, okay, and suppose the dimension of V is equal to n. Okay. Then, given a basis B of V for any vector V in V, there exists a unique coordinate. This is, well, a unique x in f n such that V is equal to Bx. What does it mean? By B here, we are just meaning the set of vectors, v1, v2 to vn, say, and this one is giving the linear combination. So what we mean by this is that if you write B as v1 dot dot vn and x as, say, a1 dot dot an, by this notation we are just meaning that V is equal to A1 V1 plus dot 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 plus AN Vn. Okay, only that. Okay, all right, and this x would be called the coordinate vector of V. Okay. This x is defined to be the coordinate vector or the coordinates of V. Okay. So, in whichever vector space V is, the coordinates are always going to lie in Fn, that is, so F is a field and N is, Fn just means the Cartesian product of F with itself n times. Okay. Now, here we defined what is a linear transformation, right? A linear transformation which is bijective has a particular name, it is called an isomorphism. Okay. Isomorphism is a linear transformation, a bijective linear transformation. Isomorphism of vector spaces. Okay. A bijective linear transformation. So, as with vector spaces, we gave two examples. For isomorphism, we already gave an example. So, it is an exercise, it is an easy exercise for you to check that the map from V to Fn, which sends a vector V to its coordinates, is an isomorphism. Okay. That is, it's injective and it's surjective. Okay. And now we will define what we mean by the matrix of a linear transformation. So, till now the definition, the concepts we saw is what is a linear transformation, what is a coordinate, and what is an isomorphism. Okay. So, if any of you are having trouble understanding what is a linear transformation or what are coordinates or what is an isomorphism, stop me immediately and ask for it again. Now what were, okay, matrix of a linear transformation. Matrix of a linear transformation. Okay. So, suppose T is a linear transformation from V to W. Okay. Now, let B be a basis of V and let D be a basis of W. Okay. We are going to write the matrix of the linear transformation T in terms of B and D. Okay. At first, yeah? No, Manideep, please tell me. Yes. Right. Of course, yes. Well, what you are doing, you are taking a entry-wise map, right? You are mapping just A, B, C, D C, D, and here you have addition, scalar multiplication. Here you have addition and scalar multiplication. Just check whether they are compatible. That is, if you take any linear combination of matrices here, whether they are being mapped to linear combinations of the corresponding vectors, then it's a linear transformation first, and then check whether this map is bijective or not. Okay. So is it possible that things go to 0? I mean, some matrix is being mapped to all 0 things, even if this is not 0. It's not, right? So it's an injective thing. And surjectivity, so given any such thing, you can always construct such a matrix. So it's surjective. It's a trivial example. Yes. We are going to define it, what a linear transform, what the matrix of a linear transformation is. Yeah.
His confusion lies in that he is thinking of multiplying the vector by matrices, but actually we are multiplying the coordinates of vectors by matrices.
Yes, so it will be soon clear once we define it. Let me define it first. Okay. So this is just mapping the vectors V to their images, some W. Say. Okay. So that means a vector V in V, you can write it as V is equal to Bx, where x is the coordinate of V, right? And then since linear transformation is compatible with taking linear combinations, that means T of V will be T of Bx, right? And what is x? X is just the coordinates, the coordinates of V. That means the coefficients of the basis vectors. Okay? So Bx just represents a linear combination of the basis vectors, right? So the compatibility of T with addition and scalar multiplication, that is with linear combination, will mean that this is just T of Bx. Okay. Well, if you are all of you convinced, or should we do it explicitly? Okay, for the first time we can do it explicitly. For the next times maybe it would be more apparent. So this is V1 V2 to Vn, and then V is equal to A1 V1 plus dot 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 plus An Vn, right? So T of V is equal to T of A1 V1 plus dot 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 plus An Vn, right? Okay. And then we said that it is compatible with linear combinations, right? So this is A1 T V1 plus dot 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 plus An T Vn. Okay. And that means we are just having T of, so now if we go back from this notation to this one, it will be like T of V1 dot 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 T of Vn times A1 dot 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 An. So this is the hypervector, and this is just denoting the linear combination of these elements. Okay. So that's what we wrote here. This is T of B, and this is just x, the coefficients. Okay. Yes.
Is it appropriate to write T of B because it's a map from V to W, right?
Yes, but it's like, I mean, so you suppose you have a map from F from R to some other set S, and then by F of R you mean the image of R, right? So there we are meaning that it is the image of the particular, so okay. So it is T of, by T of B we are meaning that it is the image of this particular set. So T of B is, by this we mean that it is the image of B. Okay. Okay, so we expressed V in terms of the image of the basis and its coordinates. But remember that D was a basis of W, right? So TV you can also express as a linear combination of the elements of D, right? Suppose this is equal to dy, where y is a coordinate vector of TV. Okay. So what we get now, TV is dy, and that's also equal to TBX. Okay. Right. Okay. Up to this, everybody is with me, or any confusion about any notation or anything? Okay. Now, B we said that this is the vectors V1 to Vn, right? So TB is just the image of V, which is T of V1 dot 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 T of Vn, right? And suppose D is given by W1 dot 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 Wm. So each of these V1 to Vn, we can express this as a linear combination of this W1 to Wm, right? So let's express them here. W1 dot dot Wm, this times, and here we will express T of V1 dot 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 T of Vn, excuse me. T of V1 dot 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 T of Vn. Okay. So now here what we will have, the linear combinations which are giving those, right? So some column vectors with which we are multiplying this hypervector, so that the first one corresponds to this, the second one corresponds to this, the second one, and so on. Okay. So suppose the first column vector is A1, the second column vector is A2, the last column vector is An. Call this matrix A, okay. And then this one is just D. Okay. This is the vector, sorry, not vector, this is a hypervector corresponding to the basis D of W, right? And this is nothing but the image of our basis B. Okay. And this matrix, what is the dimension of this matrix? There are n columns and m rows, right? So this should be m cross n. And this matrix will be defined as the matrix of the linear transformation T. Okay, let's write it down somewhere again. Yes? How do we get the matrix? We are just expressing TB, the elements here, in terms of the vectors W1 to Wm. So each of the elements in TB, in the image of B, is a linear combination of the elements of the basis of D, right? Okay. So this A1 is the first. The first column of this matrix is just giving the linear combinations of W1 to Wm, which is producing TV1. The entries, these entries are corresponding to the coordinates of TV1 in terms of this basis D. Okay. These are the coordinates of TV2 in terms of this basis, and so on. Okay. So TB is equal to DA. The basis of the domain vector space, the basis of the range vector space. Okay. And this is called the matrix of the linear transformation T. Okay. Now we are going to relate this matrix, relate the coordinates of V and TV in terms of with this matrix A. So we are just going to rewrite those. We know that TV is equal to dy, which is equal to TBX, right? So we saw till now TV for any vector v is equal to TBX, which is equal to dy, right? This is Trishit, you are looking very sleepy. Please come forward. And Gayatri, could you please also come to the front? So TBX, now we know that TB is equal to dA, right? So this is equal to dAX. Okay. So we are expressing TV in terms of this basis D in two ways. One is dAX, because TV is dA by definition. This is the matrix of the linear transformation. And this one is something we started with. That is, we said that we can always represent TV by a unique linear combination of the elements of D. Okay? Unique linear combination. Okay. What does it mean? That is, you are expressing it in this manner and this manner as well. Yes, because the expression should be unique, right? The linear combination is unique because D is a set of linearly independent vectors. Okay? If there were two different linear combinations expressing the same thing, then this would not have been linearly independent. A sleeping dragon should never be tickled. You see? Please tickle him by the side. Wake him up. Please come forward. Yeah.
I didn't understand what you said last time.
Yeah. The last line? Yeah. Okay. So dy here is expressing TV, right?
Yeah, you said about linear independence of D.
Right. So now what we are having from this gives you dy is equal to dAX. Okay. What is this? A linear combination of the elements of D. D was the basis of W, right? What is this? This is also a linear combination of the basis elements of D. I mean W, right? Now both are expressing TV. Okay, some element in W, and we know that for every element in W there exists a unique linear combination of the basis vectors which represent this. Because if so, suppose this one is A1 W1 plus dot 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 plus AN WN, and suppose this is another thing, B1 W1, W1s to WM, sorry. W1 to WM are the basis vectors, that is the elements in D. Okay. So B1 W1 dot 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 BM WM. Suppose these are two different expressions, both representing TV. Okay. You can take this one to the other side, and then what you are getting a linear combination of W1 to WM, which is giving you 0. So that means each of the coefficients should be 0. That means that A1 should be equal to B1, AN, AM should be equal to BM, right? In other words, the coordinate vectors should be equal to each other. Okay. So dy equal to dx. Can I wipe this line out? Is it clear to all of you? Okay, thank you. So this is actually if and only if y is equal to ax. Okay. So we see that we are going from a vector space of dimension n to a vector space of dimension m just by multiplying with the matrix of the linear transformation. Okay. That is, a linear transformation of arbitrary vector spaces can just be considered as a multiplication with a matrix, a left multiplication with a matrix, provided we know the basis of them. Okay. Without the basis, we cannot do that. So till now, let's recall what we have done. we defined what is a linear transformation, we defined what are coordinates, what is matrix of a linear transformation, what is isomorphism. Okay, nothing else so far. Is everyone, yeah, okay. If we multiply with the dy equal to dx, d is a basis. I mean, d is just a hypervector. It's just this hypervector. Okay. Yes. D to be bijective. What it means by bijective? I mean, d is a basis. D is a basis of W. That you are mapping. Well, you are making me answer the question that I asked about isomorphism. So from Fn to V, you are having not V, sorry, W, and this one was Fm. Okay, and here you had D, right? Some basis given to you. Here you are having X. This X is being mapped to dx. Okay, so every column vector here is going to dx, right? And then the question was that show that this is an isomorphism. And this is an isomorphism because D is a basis. You cannot have dx equal to dy where x is not equal to 1. Because if x is say a1 dot dot an and y is b1 dot dot bn, we said that such a thing corresponds to this linear combination a1 w1 plus dot 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 an wn being equal to b1 w1 plus dot 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 bn wn. Okay, is that possible? That is a1 w1 dot dot an wn equal to b1 w1 plus dot 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 bn wn, where x and y are not equal. That is, this one and this one are not equal. Why not? No, after this, just exactly. So from here, we are getting that a1 minus b1 w1 plus dot 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 plus an minus bn wn is equal to 0. A basis means that they are linearly independent. So all the coefficients should be 0. So ai's should be equal to pi's, and that's why this is indeed a bijective map. But nevertheless, thanks a lot for the question, because otherwise I would have assumed that everybody understood this. So, but now I hope this is clear to you. And anybody else, I mean, why this map is a bijection? Is there any doubt about this? Tell me again, we'll go over this. Gayatri, is this clear to you? Sumbi? That is, we are mapping a column vector to a linear combination of the basis vectors by the elements of this column vector. So x is just equal to such a column vector, which are giving you the coefficients of the linear combination of these basis vectors. Okay, w1 to w. So dx just denotes that d is this w1 to wn, and these are just giving you the linear combinations corresponding to that. And these two cannot be equal, because if they were equal, then that contradicts the linear independence of w1 to wn. So, what is a matrix of a linear transformation, and how the coordinates change under a linear transformation? They are changed by just multiplication with the matrix of linear transformation. Okay. Now, given a linear transformation, we define what is kernel of T and what is the image of T. Okay. Are you familiar with this notion kernel? So these are, so T is a map from V to W. Then kernel of T is the set of all V in V such that T of V is equal to 0. That is a set of all the vectors which are being mapped to 0. Okay. To the front, please. Excuse me. You. Your name, please. No, you. You in blue shirt. Pranav, could you please come to the front? Yes.
So what is the difference between kernel of T and null space of T?
Well, if A from Rn to Rm is giving you a map by left multiplication, A is a matrix, then indeed the kernel of A, this we call as the null space of A. Okay, null space we define for a matrix. Okay. No, here A, I mean by A we are just defining the left multiplication by A from Rn to Rm, and then kernel of A, I mean this map, well you can call it maybe TA, and then you can write this is TA, that is left multiplication by A, which is giving you null space of, I mean which is the same as the null space of A. That is the set of all the vectors which are sent to 0 by left multiplication with A. Okay. And image of T is the set of all the W's in W such that W is equal to TV for some V in V. Okay. So all the vectors which are images of some vector in V. Okay. So Monideep, what is the corresponding concept for matrices then? It is the map, I mean, it's the image of Rn under the multiplication of A, right? So you are considering A, I mean, so this one would be, so image of TSA is the set of all y's which are equal to Ax for some x in Rn. Okay. This has a name. What is that? Very good, Pranav. Column space. Column space of A. Okay. Because you are taking linear combinations of the columns of A to get this the image of this linear transformation which is defined by the left multiplication with A. Okay. All right. And now we define what is nullity of this linear transformation T. This is just the dimension of kernel T. Now when we write the dimension of kernel T, that means at first that this is a subspace. How do you get it's a subspace? At first it's inside V. So what we have to show that it's a subspace? Exactly. Now you are taking linear combination of two vectors, both of which are mapping to 0. So any linear combination is mapping to 0 because T is compatible with linear combinations, right? And then rank of T is equal to the dimension of the image of T. Again, that means image of T is a subspace of W, right? Samarjit. So why is this a subspace of W? Yes. Take any linear combination of the elements here as well. So suppose W1 and W2 both are in the image. That means there are TV1 and TV2. I mean W1 is equal to TV1 and W2 is equal to TV2. Take a linear combination of V1 and V2. So if you have W1 is equal to T of V1 and W2 equal to T of V2, that means AW1 plus BW2 is just T of AV1 plus BV2, right? So there indeed, I mean you see AW1 plus BW2 is then again an image of some vector in V. Okay. So image is also a subspace and therefore defining their dimensions makes sense. Okay. So once we have defined this, then the dimension formula, which you have perhaps seen already for matrices, says that the dimension, okay, T is a map from V to W, then nullity of T plus the rank of T is equal to the dimension of V. Okay. It's called the dimension formula or Rank-Nullity theorem. Okay. All right. So the proof is rather straightforward, and the proof technique is very useful. We will use similar things again, okay, at least in 2 occasions. At least in 2 occasions, one of which you can see perhaps before the midsem, one after. Okay. So here, what we do, we begin with the kernel of the map. Okay. So here's the proof of this. Okay. Let B0 be a basis of kernel T. Okay. We extend it to a full basis of V. Okay. Let B, which is an extension of B0 by appending some more vectors B1, be a basis of V. Okay. Shivam, please follow the proof, because we said that we are this technique we will use again and again later. Okay. So this is a basis of V, and now look at the image of this. Okay. So suppose you apply T on this. What will be T of B? T of B would be just, this is the set of images, right? So this will be just T B0 and T B1, right? This was the basis of the kernel, and these are the appended vectors, which is making it into a basis of the entire vector space V. Okay. Now what can you tell about T B0? Louder? Yes? Yeah? Again? It is? 0. Because? Very good. What's your name? Savit. Okay. Thank you, Savit. Because all the elements of B0 are in the kernel, right? B0 is the basis of the kernel. So all the elements should go to 0, right? So you can write this as 0, that is the set of 0 vectors, and then T B1. Okay. All right. Now the claim is that the image is spanned by this one, TB1. Not only that, TB1 forms a basis of the image. So at first, why the image should be spanned by TB1? Yes, again? Yeah? TB0 is, right, TB0 is 0. So any vector you can represent as a linear combination of B0 and the elements in B0 and B1. But everything in B0 is going to 0. So what remains are these ones and the linear combinations of them, right? So if you write a vector V in V as V is equal to B0 x0 plus B1 x1, okay? That is, this is some element, some element in some fn, the k, let this be the dimension of kernel T, and then x0 is in the field, k copies of the field, and x1 is in fn minus k, say. Okay. Then you apply T to this. What happens? You get TB0 x0 plus TB1 x1 because T is compatible with linear combinations. Okay. This entire thing is equal to 0. So you get that TV is equal to just TB1 x1. Okay. So yeah. Why do we take? Oh, because, well, at first I have to define what is n. So n is the dimension of V. Okay. And then since this and this is making up a basis for the entire vector space, so the cardinality of B0 and B1 together is n. Now there are k, I mean the linear combination of this will have k coefficients, the linear combination of this will have n minus k coefficients, and that's why we took it from n minus k. So indeed TB1 spans image of T. Now suppose they are not linearly independent. Okay, the elements in TB1, if they are linearly independent, we are done, right? So suppose they are not linearly independent. What does that mean? Some linear combination of them is going to give you 0, right? Okay. So if TB1 is not linearly independent, then there exists some y in R, or not R, we are working with the general field f n minus k, such that TB1 y is equal to 0, right? That would mean that TB1 y is equal to 0. T is compatible linear combinations, recall? In other words, B1 y belongs to the kernel, right?
So you need to specify the non-zero one.
Yes?
You need to specify that y is not.
Ah, right, yes. So as y in this minus 0. Thank you, Vishesh. Indeed, we need this to say that they are not linearly independent, they are linearly dependent, right? Now this one means that this belongs to kernel of T. So you can express B1y as some B0x, right? That is, B0 was the basis of the kernel. So some linear combination of the basis vector would give you B1y, right? So that means that B1y is equal to B0x for some x in f per k, right? And what does that mean? What was this? B1 to B1 and B0 together they were forming the basis of V, right? So this one just means that you are getting a linear combination of the basis vectors which is equal to 0. In other words, all the coefficients should be 0. So this is not true unless both y and x are 0. Okay. So that implies y equal to 0 and x is equal to 0 as well in the corresponding spaces. Okay. Okay. So that's a contradiction because we assume that y is non-zero. Okay. In other words, we see that TB1 is indeed linearly independent, right? So now this is rather simple then. We are proving this by because what is B1y? It's the linear combination of the elements of B1. What is B0x? Linear combination of the elements of B0, and they are equal. That means if you take this to this side, you are getting a linear combinations of the elements of B0 and B1. But together B0 B1 was forming a basis of V. So B0 and B1 are linearly independent. No linear combination of their elements can be equal because that would give you a 0 linear combination of the elements of the basis of V.
But B0x is already 0 for all.
B naught x is, no, it is not already 0 for all x. B naught is a basis of the kernel. All you know is that T B naught x, T is equal to 0, but B naught x is not equal to 0. Okay. Okay, now what we have, consider these two coordinates. What they add up to? The coordinate of B0 and B1, dimension of V, right? And then this one is just a nullity of T, right? The kernel of the dimension of the kernel. So nullity of T, and this one is equal to T B1, right? These two things is exactly the same, because T of B1 is just denoting the image of this one. Okay, this is equal to dimension of V, right? Yeah.
How do you prove that that is equal to the dimension of the column space?
Which one?
T of
T of
cardinality of B1, cardinality of T of B1, all of them are dimension of the column space.
space for this particular case where we are considering the matrices.
Row space or rank?
Column space. We will prove that column rank is equal to row rank, but later, not now. And we will repeat this technique there, okay, in a different manner. But now we are not proving that row rank is equal to column rank. Till now, for us, rank of a matrix is column rank. Okay. So TB1, what is this? This coordinate? Why? Yes. So this is TB1 is forming a basis of the image, right? So that means this is the dimension of image T, right? And what is the dimension of image T? The rank of T. Okay. Rank of T. Okay. So we got that nullity of T plus rank of T is equal to dimension of V, as we promised here.